chemical dynamics. This chapter explains rate of reaction. What is meant by rate of reaction? A reactant gives rise to product. When time is 0, that means when the reactant is about to start the reaction, let concentration of reactant will be small a and concentration of product will be 0. At t time, product will be formed, its concentration will be x, and the remaining concentration of reactant will be a minus x. Now we can define rate as dx by dt is equal to minus d of a concentration by dt. That means this dx is the change in the concentration, dt is unit time. So rate of reaction can be defined as change in the concentration of reactant or product in unit time, or decrease in the concentration of reactant in unit time, or increase in the concentration of product in unit time is called the rate of reaction. Here gradually concentration of A decreases, so we will write minus. Gradually concentration of product will increase, so concentration change in the product will be taken as positive. Now let us see how to write rate of reaction for some reactions. Suppose 2A gives rise to products, dx by dt is equal to minus 1 by 2 because there are 2 moles, d of A concentration by dt. Suppose 2A plus 3B gives rise to products. For this reaction, dx by dt is equal to minus 1 by 2 d of A concentration by dt is equal to plus 1 by 3 d of B concentration by dt. A plus B gives rise to 3C plus 2D. For this reaction, rate is equal to dx by dt is equal to minus 1 by 2 d of A concentration by dt is equal to minus d of B concentration by dt is equal to plus 1 by 3, because here C is the product, its concentration will increase, so we can take plus d of C concentration by dt is equal to plus 1 by 2 d of D concentration by dt. Now let us see what are the factors affecting rate of reaction. The first factor, nature of reactants. There are mainly 2 types of reactants: ionic reactants, covalent reactants. In ionic reactants, reactions are fast, so for such reactions rate is high, whereas in covalent reactions are slow, so rate is low. And the second factor, concentration of reactants. Naturally, if concentration increases, rate of reaction increases. If concentration of reactant decreases, rate of reaction also decreases. The next factor is surface area of reactants. If surface area increases, rate of reaction increases. Next factor is temperature. Most of the reactions, if temperature increases, rate of reaction also increases, because the increase in temperature provides amount of heat which is sufficient for energy of activation for the reactants to be participate in chemical reaction. And the next factor is catalyst. Generally, two types of catalyst we will discuss: positive catalyst and negative catalyst. Most of the catalysts are used for a positive increase in the rate. So positive catalyst increases rate of reaction, negative catalyst decreases rate of reaction. In some reactions, light is also one of the factor which can affect rate of reaction. Photochemical reactions, they require light. So all photochemical reactions occur only in the presence of light. That is the factor which can influence rate of reaction. Now we will see what is order of reaction. For example, A gives rise to products. Its rate will be written as K A concentration power 1. Here K is rate constant. This equation is called the rate equation. Rate equation means an equation which gives relation between rate of reaction and concentration of reactants. For example, take this reaction, 2A gives rise to products. We will write R is equal to K A concentration power 2. For example, 3A gives rise to products. For this reaction, R is equal to K A concentration power 3. Here the power 1 is called order of reaction. In this reaction, 2 is called order. Here 3 is called order. Suppose there is another reaction like this, 2A plus B gives rise to products. Its rate can be written as K A concentration power 2 B concentration power 1. Here order will be taken as 2 plus 1, that is 3. Hence order can be defined as it is the sum of powers of concentration terms in rate equation. Thus order is sum of powers of concentration terms in rate equation. Let us see some examples for different reactions which follow different orders. Zero order reactions. All photochemical reactions, they follow zero order, and heterogeneous reactions, they follow zero order. Let us see examples for first order reactions. Decomposition of N2O5. It follows first order. Decomposition of hydrogen peroxide. It is a first order reaction. Decomposition of ammonium nitrate. It is a first order reaction. Decomposition of benzene diazonium chloride. It is a first order reaction. And N-chloroacetaldehyde, acetonylide. Its conversion to parachloroacetanilide is a first order reaction. And hydrolysis of ester in the presence of acid. It is a first order reaction. Inversion of sugar. It is a first order reaction. And SO2Cl2 decomposition is also a first order reaction. Some examples of third order reaction. Nitric oxide reaction with chlorine, 2NaCl with bromine to give NOBr with O2 to give NO2 with H2 to give nitrous oxide and water with deuterium to give nitrous oxide and D2O. Also reduction of ferric chloride by stannous chloride. This is also a third order reaction. Let us see what are the characteristics of order of reaction. Order, sometimes order may be 0 also, sometimes it may be fraction also, and it may be 1, 2, 3, like such values are all possible for order of reaction. And this is experimentally determined quantity. Sometimes order may be negative also. We will see what is molecularity of a reaction. A reaction may take place either in single step or in several steps. Among these several steps, one step will be slowest compared to other steps. In this slowest step of reaction, which is also called rate determining step of reaction, how many molecules are participating, number of molecules participating in rate determining step of reaction is called molecularity of the reaction. See what are the characteristics of molecularity. Its value may be 1, 2, 3 like that. If 1 is there, unimolecular reaction. If its value is 2, it is bimolecular, trimolecular, etc. It will never be 0 value. It will never be fraction value. It will never be a negative value. This is a theoretically determined quantity. It can be determined from mechanism of the reaction. Now we will write equations for different reactions. For zero order reaction, we will write dx by dt is equal to k a minus x power 0. For first order, we will write dx by dt is equal to k a minus x power 1. For second order, dx by dt is equal to k a minus x power 2. For third order, dx by dt is equal to k a minus x power 3. And for nth order, dx by dt is equal to k a minus x power n. Let us see equations of rate constants for different reactions. For zero order, k can be written as x by t. First order reaction, k can be written as 2.303 by t log a by a minus x. For second order reaction, k is equal to 1 by t x by a into a minus x. For third order reaction, k is equal to 1 by n minus 1 1 by a minus x power n minus 1 minus 1 by a power n minus 1. For nth order reaction, k is equal to 1 by n minus 1 1 by a minus x n minus 1 minus 1 by a power n minus 1. Let us see units for different reactions. For zero order reaction, unit for k is mole liter inverse second inverse. For first order reaction, k is equal to second inverse. For second order reaction, k is equal to liter mole inverse second inverse. For third order reaction, k is equal to it is liter square mole power minus 2 second inverse. Whereas for nth order reaction, k is equal to liter power n minus 1 mole power 1 minus n second inverse. Let us see half-life equations. For zero order reaction, T half is proportion to initial concentration. For first order reaction, T half is proportion to a power 0, that is T half is not dependent upon initial concentration, but T half is equal to 0.693 by rate constant. For second order reaction, T half is proportional to 1 by a. For third order reaction, T half is proportional to 1 by a power 2. For nth order reaction, T half is proportion to 1 by a power n minus 1.